Okay, I'm recording now. Well, let's minimize videos. Okay, well, hi, how are you? Can't complain, can't complain. So welcome everybody. So my name is Jochen Rehmann. I'm going to be your instructor for the summer semester. It's a great pleasure to be here. That's the third time, I believe, I'm teaching this course, and it's always fun. And we're going to have fun coding a little bit in R. We're going to have fun talking about statistics. So a little bit about myself. I wore a lot of hats in my life. I studied medicine in Austria, came here in 2007, did a PhD in medical science, and basically dedicated my life and my career to research. It's mainly sort of an epidemiological research in chronic kidney disease with a focus on dialysis therapy. So I work somewhat in the biotechnology world, but my focus is really epidemiological research. So I'm a full-time researcher. I'm an administrator at a think tank for a dialysis provider. I truly enjoy what I do. And now as an additional passion, I adopted teaching as an additional task in my life. And yeah, so I like what I do. I love programming R. I started programming, so I have a longer history with programming, but basically I started programming R sometime in 2010. And transitioned over from SPSS. So many of you know that there are different statistical softwares. SPSS, particularly in the psychology world, very popular, used quite often, less popular when it comes to big data and public health research. There it's more SAS or R. Or when you go then towards machine learning, AI, you basically will encounter Python. Python is a whole different animal. So basically you have SPSS, that's statistics only. SAS is kind of a hybrid, but it's also very pricey. And then you have SAS is really good with big data. You got to give it to SAS. I do not like the syntax. Hi. I do not like the syntax. I'm not a big SAS fan, and I'm also no good at it. But basically, it's very good with big data. And it's also used for that purpose. When it comes to R does well with big data as well to some extent. There are some limitations. As soon as you have data sets that are somewhere in the realm of like 10, 15 gigs, it will have an issue. So that's the bitter truth. Python is a little better for that, but also has its limitation when it comes to big data. But there are also packages for that where you basically utilize the data in a different format. But that's too much information at this point. Good. The real beauty of R and Python as compared to SAS and other commercially available softwares is that it allows you to import packages. And these packages can be programmed by anybody. We could create a package for this course, which is actually something we could think about later this semester. So let's see how things go. So you can create a package specific for the project, package specific for your institution, specific for the class, or specific for your PhD project. And that's essentially where the beauty comes in. So you think of state-of-the-art statistical methods. Statistics is a field that is evolving, very fastly evolving, essentially. New methods are being developed, particularly now in the realm of machine learning and AI. You can imagine how much fluctuation and how much change there is in the community. And you can create basically a package quite easily. So if you think about, as the end user, about analyzing data and you want to use state-of-the-art methods and you're really good in statistics, you could hypothetically have the package of a PhD student, I don't know, from Singapore, from Australia, wherever, download it on your computer and use his or her package for your purpose. So it's becoming, we're at the time of absolute information and open data and open sharing. So you have access to a lot of these things that are being programmed nowadays. And that's really the beauty of R and Python, because it's open source. You can alter and manipulate a lot, and a lot of responsibility is basically on your shoulders, what you can manipulate and how you can bring that software to use. And that's really quite fantastic. Okay, so I started in 2010, give or take. I teach it in various classes, and I like the software. I like the syntax. It's quite intuitive, I find. You will not find it intuitive at first. You will take your bit, but it will become intuitive. I think by the end of the class, you will kind of have a good grasp on how to program simple syntaxes. And that will be also part of the outcome of this class, essentially. So by the end of this class, the expectation is that you will write a final report that basically summarizes a public health topic from the NHANES study. So the nutrition, health, and examination study is one of the largest public health studies in the world. And it's the mother of all these public health studies in a way. It started like as early as the 1990s, and they basically characterized the entire United States. So you have data in there, which is quite versatile from different fields. You have from bone mineral density data to body composition data to lab parameters. You have all data represented in this data set, and it's publicly accessible. So you go on the CDC website, you look for specific data sets, you can download them freely on your computer. So it's really great data. You have a link of the NHANES A package in R on your canvas. That is for you to download to activate in R, and I can show you how. And you will automatically get this data queried and downloaded. That will all work automatically. So particularly the first sessions, everything will be kind of automatized. So you won't have to import data yourself. You just have to export some files, and we will get started with that today. You will create your first plots and your first PDF files that will show you already how versatile and how functional and how useful R can be. Good. Later on, we're also going to import some data because you also need to know how to import files. And that will be a bit more challenging because you need to understand folder structures. You need to understand how R looks at folder structures and essentially how it reads path names to specific files. That can be a little bit of, can be a hassle, but we'll get over that. Good. I want to spend a couple of minutes to aid you in attendance. Not that I'm grading you on the attendance, but I want to attach names to faces, and I want to hear some thoughts about you and hear about your experiences with statistics. So I hear there are some basic statistic knowledge, and I think it would also be great for me to understand what knowledge you have in regards to mathematics, statistics, because I will use terms, and if I use words that you don't know or you don't really understand, please let me know. So when I use the word integral, does everybody know what an integral is? Integral. When you integrate a function. Yeah. What? Yep. Yeah. No. No. Okay. All right. It will come at one point. So we will talk about the integral. Okay. So let's do this quick. Okay, attendance. All right. So Ebenezer Ajao. Yep. So what is your background in statistics? What's your background?
Yeah, I have just basics background. I have just basic background.
Basic.
Yeah.
Okay. Okay. And you just started? Or? Okay.
Before I use SPSS.
SPSS you did use? Okay. With the syntax or just data properly? Okay. All right. Then there's Natania Birnbaum. Hi, how are you? Any statistic background exposure?
Well, I've never actually taken a statistics class.
Okay.
Proficiency in Python and a little bit of experience using it for statistics.
Okay, very nice. Python. Okay, very good. So you're already way ahead of the curve. That's good. So she's the one who you have to ask for help when the syntax doesn't work. Okay, thank you. Okay, Shreya. Shreya?
I have actually statistics, a subject of
Okay,
for Python.
okay, very good. You're gonna call me out and you gotta correct me for something. Okay, then we have Saruhi. Hi.
So I'm just doing it.
Okay.
I want to say from the start.
Okay, that's fine. That's fine. No worries.
Is learn some basic.
Okay,
Like that,
sounds good.
but I'm all in first.
Sounds good. Okay, great, great. Thank you. Okay, then we have Jenny. Hi.
I don't think I have any background in the maths, but I did use excuses very basic for my research in my undergrad.
Okay, what was the reason then?
It was about diabetes.
Okay,
But I had to collect data. So that was a professor for me. I only did 30 minimum.
okay, okay, sounds good. But SPSS, I knew there's gonna be some SPSS package. Yeah, so R will convince you it's the better software. Okay, thank you. Now we have
It's just.
Manfred. Manfred. Okay,
Yeah, hi. So
Hi.
I don't really have background in biostatistics, but I'm interested in this subject. Like right now, I'm working as a research assistant in biochemistry and chemistry lab,
mhm,
and there we are researching on proteins and exporting data and stuff. So I'm just looking forward to this program so that I can, like this program be helpful in order to understand research.
okay. Well, it certainly will. It certainly will. Okay, thank you. Yeah, R you can use in many instances, including in research labs, definitely. Then we have Vivek.
Yeah. Hi.
Oh, hi.
So in my undergrad, I had a course called biostatistics.
Okay.
The basic composition of biostatistics, and I have a very basic knowledge of SAS programming and Python.
Okay, very good, very good. So R is going to be easy for you. So those of you with a little bit of Python background, it's going to be an easy transition. So at the end of the day, I did have students who preferred Python over R. So if you rather program it in Python, I have no objections if it comes to the same means end, so to say. So, but if you rather work in Python, I just can't give much support in Python. I'm not overly proficient. I speak it a bit, but not as good as R. Okay, but up to you, really. Okay, thank you. Then we have Sayanto.
Hi.
Oh, hi. Oh, yeah.
So I have a basic background of Excel.
Okay.
Statistics.
Okay.
Similarly, I'm doing a research assistant check, where again I'm using Excel to analyze the data.
Yeah.
All things are on Excel. So this is completely new for me.
Okay. Okay. Well, if you have particular use cases that you want to discuss, we can do that after hours or before. We can definitely do that. Okay. Thank you. Then we have Chris. Hi.
No background whatsoever.
Okay.
With this, I took a computer class in high
Okay.
school,
Okay. Good.
so I know like that much. But high school for me was over 10 years.
Okay. Sounds good. Well, we're gonna refresh that. No, but it's gonna be fine. We're gonna go step by step, and we'll see how things go, and we can repeat if needed. Okay, great. Then we have on Zoom, we have Shay.
Hi, how you doing?
Good, how are you?
So I don't have much of background in computers, but I've done statistics in college, but not much more than that.
Okay, great. So that's gonna be a little bit of a repetition for you, probably nothing much new. New is gonna be then the R portion of it.
Yeah.
So, okay, great. It's gonna be fun. Thank you. Then we have, oh, ladies first, Talia.
Hi, in undergrad, mainly the first year, I did take some data science and computer science programming courses where we learned Python primarily.
Yeah. Oh, wow, nice. Okay. So also accounts for you. If you rather do Python, that's fine with me. If you prefer Python over R, but the support is more R centric. But yeah, thank you. And then we have Avior.
Yes. I took statistics as well in undergrad, and in high school I took a Python course, but I don't recall much of it. So
Okay, sounds good. So that's going to be a refresher then. All right, thank you. Okay. All right, so that was everybody.
I'm here too, just letting you know.
Oh, hi, Daniela.
Yeah,
okay.
hello. Hey,
Hi. Any background in statistics?
no, but I also in high school learned HTML and C++.
Okay, that's quite advanced. Yeah, so that's the basis for R. Okay, but the application of R is new.
Yes.
Okay, great. So it's going to be fun. All right, thank you, Daniela. Okay, so you all have seen the syllabus. So the entire class is basically on Canvas. That's also the primary mode of communication. If you want to reach out to me, there's in the discussion, and we get there later, there's in the discussion a respective tab where you can basically ask me questions. So if there are questions with syntax in R, it's most efficient that you basically post it on the discussion board and you shoot me an email and say like, hey, I posted something on the discussion board. I will try to monitor it regularly, but sometimes I may not. And if I don't react within 1 or 2 business days, please shoot me an email too. The reason why I would prefer it to be a priori in the discussion board is because everybody can benefit from it. And that's kind of, I don't want to make it, it's not an online class, it's an in-person class, but it's just for the sake of efficiency. It's better to have it in a hybrid kind of situation. Good. I have on the modules, everything organized for each module. So we're today at module 1. You basically have a structure where we basically have a lecture part, which basically has whatever spreadsheet is necessary for that particular lecture with a little code. If necessary, there is a PowerPoint presentation, which is the theoretical part. Then there's a discussion topic. For each lecture, there will be 1 discussion topic that will be graded, and I would ask you to please comment on the discussion post. So watch the video. There are hand-selected videos that are interesting to watch, and give me a reasonable comment to it. Sometimes there's a specific question, what do you think about AYC? Or give me something that is reasonably in the context, something that shows me that you have watched it, comprehended it, and had a reaction to that. So it's a low-hanging fruit, a couple of low-hanging, easily earned points. Then we have the practice lab. Practice lab is also each class. So we essentially will have some codes that are specific to the lecture. And then there are the practice labs. That's basically a specific question and exercise that either will have some code that is being provided to you. There may be a part where there's no code and that you have to work on yourself autodidactically based on what we discussed in class. It's not super hard, it's not super complicated, low-hanging points, but again, requires you to submit your code, not only the code, but essentially also the printout of your code. And I will show you how to generate that. So there's also a practice lab code attached to that essentially addresses most parts of that practice lab. Good. So this is the class per se. Then for the syllabus, there's this all spelled out. So as said, 3 main objectives. So the idea is here really to explain the roles of probabilistic models, which we're not getting too deep into probabilistic models, but we're getting into model building. We're getting into regression analyses. And we're getting into multiple regression analysis. We're not going into the realm of probabilities with these models because we just don't have the time. Usually when I teach it in either fall or spring, I also get to the basics of predictive analytics, and we get to do logistic regression as well, which is that's the point when it becomes a probabilistic model. Then the design of observational studies and experiments with appropriate scope of inference. That means that you know how to look at data and you know how to ask your data questions and how to conduct the research experiments, providing you with data that could answer your specific questions. So that's kind of part of that course as well. We will not be designing studies, prospective studies, but we will be designing analyses and analytic approaches, which is somewhat restricted because we only have enhanced data, which is cross-sectional in nature. But I think one part of it could be that in the discussion of your final report, you could kind of allude to future ideas of where this research could be going down the road. You will have with the enhanced data set, and we will talk about the final report in a second, you will have ample opportunity to essentially select interesting combinations of variables and study interesting actual real signals, right? Because this is real data. Enhanced is real data that was collected over the last 20, 25 years in US citizens. With methodological approaches, you can alter this data and you can give it weight and you can adjust for certain sampling strata. In that way, you can basically account your research to the entire US population. And that's a statistically, how should I say, a statistically, not manipulation, a statistical handling of that data by assigning weights that you can extrapolate it to an entire population. I will talk about that a bit more. Well, I'm not sure we're gonna get to the weighting, but hypothetically you could do that. And then there's the collaboration piece. The idea is also that you kind of understand the jargon, you kind of speak the language that you can speak with statisticians, epidemiologists, as well as researchers in a way that you can connect everybody on the table together and get on the same page with everybody. So the book that I'm requiring here, as for reading, so the required reading, that's actually an excellent free of charge open source statistic textbook. I'm going to minimize this. So this is free of charge. You can download it from openintro.org. We're going to do some of the exercises from OpenIntro. And that's actually, it's a very good textbook for you to read up in more detail. It's all in the syllabus and yeah, it's a really good book. Good. Office needs to be pre-installed. If you don't have Office, that's okay, because Yeshiva actually provides you with an Office 365 online that you can use. So you have the full Office suite at your disposition. We talked about Data Camp. All of you should have received an invite for Data Camp. If you did not, please shoot me an email and I add you to the list. So 3 courses are assigned to you. So there's a first like experience Data Camp course. Then there's a second one, Intro to R, and there's a third one in that context that is Intermediary R. And this will kind of make you understand how R works and ticks. And that will be very insightful. And it will help you to essentially bring that then into the practice lab and your final project. So we have practice labs. We have with each of our lectures, we have a practice lab. The total score for this course is 1,000 points. We have 10 practice labs. That was 100 points. That's basically in class, maybe finalize it at home, but it should be submitted by the end of the day. Then we have the graded lab. For that, you will have a week time. That's challenging you to some extent, that you sit down, you work on your R code, and it's not super complicated, but it will take you a little bit of time and investigation how to do that. The Data Camp training, that's also allocated 10 points. Then we have the discussion points, that's the easily earned points, that's 100 points. Then we have 3 quizzes, not super complicated, but basically just testing your knowledge, how you come along with the material in class. And then we have the final project, and this is really the fun part. So the final project basically consists of 4 different parts, which is here a first draft, and that is due mid of July, I believe. And that first draft should really contain an analysis plan, as well as a first draft, a skeleton of that final report. So you should know probably by mid-end July what parameters you're interested in, what the research question is that you're interested in and that you want to focus on. So I would start probably with getting this data set down from the package, and I can show you how. Actually, the code is easily accessible. Yeah, we get to that. So basically just study the parameters, study the package, the manual in which you will find the data dictionary. So you will know which parameters are at your disposition, and then think of research questions that are interested in the context. So there's one exemplary submission from a former student is on, just that you get an idea and a taste of what a good submission would look like. Yeah. So we have first draft, analysis plan, final report. So that's the final package. That's a little tricky because the final report is basically due on the last day of lecture. So it's a little bit, it's a time crunch. So we have 6 weeks. It's going to be 6 weeks. But at the end, we should have a good outcome. Part of that is also presentation. So you're also being asked to put together a couple of PowerPoint presentations, a couple of slides, and that's the lecture where I'm sitting in and I'm listening to your elaboration on your topics. And it should be fun. It's nice to basically present your own work, present the coding and the rationale behind your work and where you think this research could be going. So I think it's reasonable for 6 weeks. I think we can fit this all nicely. And there's a little bit of an explanation to that. Yeah, grading scale. Yeah, so it's basically you have here lined out all the different topics. There are some basic topics. So the first 4 lectures, we're going to talk about very basic topics, but we have this accompanied essentially with coding exercises for all the topics. We're getting then here to hypothesis testing and then power and sample size. We're going to just touch on. We're getting here to contingency tables and then end of July to linear regression, correlation, and multiple regression. And really multiple regression is a lot of fun. So that's kind of where this research is then probably going with the final project, where you try to explain signals that you see in data with various other parameters. Good. Okay, any questions to the syllabus? No? Okay. All right. So then let's start off with first lecture. Okay, we're talking today about data sampling, design of experiments. So we spoke about the course. We will have today an introduction and comparison of R and Excel. We outline the syllabus. We identify data types, and we talk about creation and interpretation of tables and graphs. Okay, so what is statistics in principle? What does it entail? So basically, we're looking at data collection. So you need to understand how to actually collect your data to be able to make sense out of your data and to draw inferences from your data. So, and that's usually where you want already a statistician at the table, because the statistician can tell you, how does this data need to be collected? How does it need to be organized? What's the frequency we need that? Do we need longitudinal data, cross-sectional data? How does the data look like? What shape or form? Should it be collected and then be stored? Then the second pillar is essentially the description of data. So you need to describe data. The first step of every analysis will always be that you describe your data graphically and numerically. We will be talking about various ways how to display data graphically. So that's most prominently and most well known is histograms. We will talk about that a bit today, and we will also program our own histograms next class. And so it's also numerically, we have central tendency, we have mean, medians, modes, we have variability, we have interquartile ranges, we have standard deviations. We will talk about this in more detail, that you understand what that actually means if you read it in a publication, if you read it in a report, or whatever application you may see it. Of note, you also have a class later on trials. So I actually connected with the instructor. So there's actually, we plan to interact and the methods that are being mentioned in papers that you will be discussing in class, that we can basically spend some time here and this class to discuss the statistical methodology that is used in this paper to analyze the data. Yeah, so that's description, and then we have inference. Inference is basically making a decision and drawing conclusion based on the dynamics that you see in your data, on differences that you see in your data, and associations that you see in your data. So, okay. So statistics is really old, and that goes back to old Greece, basically trying to do their first statistics, then moves on really beyond the earlier times, then into the times in the medieval ages and after, where the mathematical foundations for statistical principles were found. And you see here a picture. This is Reverend Thomas Bayes, who is the developer of Bayesian statistics. So it's actually quite interesting. So they did simple experiments, and Bayes in particular, so he did an experiment for conditional probability. So he meant to estimate the location. So he had a pool table, and he meant to estimate the location of a pool ball. You also call it a ball, right? Of a pool ball on a pool table. And he would do that by basically rolling, without looking at the pool table, rolling slowly other balls somewhere on that pool table, and had an independent assistant telling him it's too far left, it's getting closer, but it's still too far left. So based on that, on this experiment, he meant to hit that other ball, and he would record all these attempts and would then, based on that, develop conditional probability, meaning the probability of hitting the ball by having prior beliefs and prior insights into where that ball is located in reference to the other ball. So these experiments basically were the foundations of statistics we're using to this day. And it's fascinating when you think about it. So the history basically informs us about how statistics were developed over the millennia. And then it goes on. It's like, I don't know whether you've seen the movie. So there's Alan Turing shown, who cracked the Enigma code during World War II. So it has a very long history. He basically used Bayesian statistics to crack the code of the Nazis. So it's all kind of intertwined, and it basically has a mathematical foundation that goes back a very long time. It's a very interesting slide. So if you have time, check it out on the website below. Okay. So, but if you go back, so basically what you're doing when you do statistics, you, in most cases or in all cases, you do analyses, except for population health studies or population studies, where you study entire population, you do analysis on a sample population. And therefore, it's important to understand the distinction between a population and a sample. So a population is really a question of definition. So you can define a population in any way you want to define it. So if you're interested in all people on the world, that's the world population, or you have a population in a country or a population in a city. when you have a sample, you essentially, you look at a subset of that population and you study that sample in a way that it gives you insights in the overall population. So you're basically equating dynamics and associations that you see in your sample to those of your population, which comes at a price. So I'm not going to go too deep into that. So a survey is a way, or a census is a way how you can quantify an entire population, but that's a little bit harder to conduct. But the US Census, for example, is one of the largest censuses in the world, which basically takes place only 10 years because it's so laborious, so expensive. So you're really basically restricted to samples to study. A single observation in a sample is basically called a record. It's a definition, it's a jargon. And when coming to the parts of statistics, so here you actually do have data that is describing statistics in New York City. What's interesting here is it's basically data in a population. So you have the population of New York City, and you see what is called here deaths per 1,000 population. And that's also a very typical way of looking at data of that kind. So basically what you do, you know a census, you know how many people lived in a city at any of these chosen years. The only thing, you don't know how many people moved away or how many moved to that city. So you have an estimate of how many people lived at that time point in the city. But what you know, how many people died in that city within a year. Given that you have a good death record system, which may not be true in New York in the 1800s, but that's a different conversation piece, but you do have a good count. So now with this count, you need to account for the fact that the population in the city varies because people move away, people move into the city. So one way to do that, that's actually the most common way, is by quantifying mortality rates. And these rates are basically quantified as deaths per 1,000 population. So what you do, you have a count. You know that at this time you had, let's say, 30,000 people die. And you know at that point you had 8 million people live in that city. So now you have 30,000 divided by those 8 million. You're standardizing the probability of death for one citizen, and then you multiply it by 1,000 to standardize it to 1,000 individuals. So that's how you quantify these rates, and you standardize it for a certain number within the population. Thereby you get a comparable rate for each year of observation, because that's how you can standardize it and compare it between different rates, knowing that the population per se will be varying. So that's descriptive statistics. That's one way of looking at descriptive statistics. Other ways on how to characterize descriptives in samples we will discuss next time. But this is one way how descriptive statistics basically can be very helpful in public health research. And what's interesting here, since you also know events that are happening certain times, you can, based on these changes in descriptive statistics, you can already assume that you can also draw inferences based out on these changes, these rapid changes in the mortality rates. You see that cholera here came with an enormous upswing of the mortality rates. Yes.
Overall statistics, but for example, during COVID, we had more deaths, right? In this case,
yes.
Taking into account that we have different environment.
Well, the situation would be the same with COVID, right? You would have populations, you would have higher event counts, and the standardization would still take place in the same fashion. So what you would see with COVID would be the same increase you had here 200 years ago with cholera, for example. So it's basically, it's reflected in these rates. And irrespective of the size of the population, a change in, so you have numerator and denominator. And if the numerator changes with the same denominator, you will see this rise of the rate. The standardization just takes out the fact that the population has changed. But you could compare the rates from 1800 in the same fashion to the rate you have seen, for example, with COVID. You could compare the rates, right? But what you really want to see, if you want to draw solid inferences, you will need to look into longitudinal data. So with COVID, for example, 2020, you would compare 2019 and then over time 2020, and then it slowly goes down, right? But the quantification of the death rates is done in the same fashion. And that's where it becomes very insightful, because these upswings in mortality rates inform public health officials and the New York City Department of Health that something is happening. And yeah, in essence, calculations of that kind were actually the birth hour of epidemiology. So epidemiology really derived from the, so the first use case of epidemiology was actually in the 19th century in the UK, where they basically found was a quantification of such rates in various sub-districts of London. They actually were able to identify a well that was contaminated with pathogen. And there was an epidemiologist named John Snow, nothing to do with Game of Thrones, but it's basically, so here's, he developed the concept of identifying the incidence rates of a disease, of gastrointestinal disease, and increase in the mortality rates consequently, to basically identify areas that are most affected. And they were able, based on that, to find the downstream of a contaminated river that ended up in a well that people would use for water consumption. So this is one of these inferences that you can draw based on data of that kind. So that's the idea. So descriptive statistics, that basically leads then to inferential statistics. Oops. And the classic inferential statistics is basically where you draw inferences about an entire population based on your sample. And the prime example that all of us have seen is political polls. So you have surveys where one TV channel has a survey institute that surveys 1,000 people. Then you have a second TV channel that polls another 1,000 people. And you get different estimates from each of these surveys. And then you use these surveys to basically come to the conclusion of what that approval rating essentially is for that particular candidate, or for that president, or for that mayor. And you basically get around this estimate, you get a certain level of uncertainty. And this is the margin of error. And this margin of error is basically, we will learn about this in like 4 to 5 lectures. That's the confidence interval, and that's the confidence interval. This is that interval within which you are, to a certain level, most commonly 95%, certain that that approval rating or that estimate will actually be in the population. So that's the definition of an estimate and the surrounding margin of error. And yeah, so these surveys are correct or not correct, but basically inferential statistics make inferences to from a sample and extrapolate them and infer them to a population. Yes. So, for example, if you were to look for significant differences, like you would sense significant differences here, because the 95% confidence interval would basically also indicate that there's a significant difference between that and that, which makes sense in some shape or form. Yeah. Well, you would need to have each individual data point here, right? So all of these are individual surveys that were done at different times. But you get a level of uncertainty. You get variability of each estimate at each time. So one survey has one estimate, second survey has another estimate, and that variability will inform you how much uncertainty I have in my estimates. Okay, so inferential statistics. What are the sources of uncertainty? So how great is the uncertainty? So there's quite some uncertainty around it. So you're somewhere in the realm of like 5% plus and minus. The sources of uncertainty can be various, can be just random sampling variability, because you call random people, you may be more likely to reach one over the other, and there may be differences. Differences may be also how these are selected. Yes.
That we can say that after this level, we can consider that the data is very good. And
yeah, most commonly it's 95%. So that's kind of generally embraced by the scientific community. There are caveats to that. So you can have a 99% confidence, a 95% confidence. You can also work with a 90% confidence, which is essentially very narrow. With 99, it gets very wide. So it's also it's a trade-off between the wideness of your interval, how much does that interval want to be? How certain do you want to be? And yeah, is there really something that is accepted? The 5% have kind of found its way into the scientific literature and community based on a statistician that actually was on the history side. On the history slide, Fisher was a statistician in the 1930s or 40s. He mentioned in one of his publications a 5% margin, 5% uncertainty that is to be accepted. And based on those 5%, and then one particular publication, the scientific literature embraced 5%. So right now, most publications state that the p-value, so the p-value is this level of uncertainty you're willing to accept that you make a wrong decision in your hypothesis test, that the p-value of 5% is acceptable. So, and this would be considered significant. Good. Okay. But how do you come to inferences? How do you analyze descriptive data? First of all, you need to understand the types of data. And there are really four large categories of data that we're looking at. So you have nominal data, ordinal data, discrete data, and continuous data. And that distinction is important because you will need to handle it differently. So nominal data can be categorically, and that would look like this. So nominal in its most commonly used form is dichotomous, so it's binary. That means either you have a control patient or you have a treatment patient, so it's 0 and 1. Or you have a patient that is still alive at the end of your study, or he or she is dead at the end of the study, then becomes a 1. So you basically assign 0 and 1 based on the condition that you that's the outcome that is defined by the outcome. Of note, you can basically do this with any parameter that you're interested in. Hypothetically, you can also recode biological sex into male and female, or 0 and 1, but by saying male gender versus female gender. So if you recode it into that fashion, you can basically recode any parameter into any parameter that has two different levels into a binary outcome as 0 and 1. So it's really the categorical data. It doesn't change just the way you're labeling it. And that's important when it comes to the interpretation, particularly in regression analysis. To illustrate that, here we have categorical data basically recoded into 0, 1, 3, and 4. So you're just assigning different numerical codes. So, but no matter what is assigned to this level of the categorical variable, it's still a nominal variable. So it doesn't change just because it's a numerical label. That's the take-home message from this slide. So yeah, they're nominally numbers, but it's a nominal variable. Then we have ordinal data. So ordinal data is basically data that follows a certain scale, a certain rank and order. So commonly found in performance scales, well-being scales, and surveys, as you will have in the enhanced data. So here, as a performance scale, from 0, fully active, versus 4, disabled, and you have the different levels in between. So that's a classically ordinal variable. The order is unimportant, the magnitude is important. The order is important, but the magnitude is unimportant, because you can't really, you're assigning each respective individual in your data to one of these categories, but the categories are basically defined by you when you define that bin, that category. Rank data is important type. Same here. When you're ranking the most common causes of death, and you're ranking heart disease as the most common cause of death, you're ranking the 5 most common causes of death as an ordinal variable. So the magnitude of the difference doesn't really matter. So you don't pay attention to the actual number. You do that when it comes to discrete data, and this is, so only the order is important. And that's important distinction, because when you come to discrete data, you have the very same data, but now you focus on the actual magnitude of that outcome. So here you focus not on the order, but you focus on the actual data. So these counts will basically be your discrete data. So depending on the perspective you're looking at your data, it's either ordinal or it's discrete data. When it's focused on the counts, then it's discrete. So this is just a way how it's commonly depicted. So you see here the ordinal data, where you have basically for each year the respective cause of death, and the expected counts are basically shown here. So that's the second variable, so to say. And it can be treated either as a nominal or an ordinal variable. If it's in order, it's an ordinal variable. If it's only the category, then it becomes a nominal variable. And here you have, again, rates. And that's, again, the standardization of the rate, standardized in the same fashion. So you have counts of a certain disease, you have a certain population at risk, and you calculate count and the population in the denominator. And you standardize it per whatever part of the population you want to standardize it to. So here it's for 100,000 individuals. Any questions to that? I think it's considerably simple. It's just basic, because it becomes important when we import data into R, that we understand how does this data look like, how does R handle it. Then it becomes quite central, essentially. Okay. Yeah. And this is basically what the positions, where the order changes based on the discrete data at hand. Magnitude matters, arithmetic applies. Yeah, important also. This data you can also arithmetically approach, so you can calculate the differences in counts. Whereas when you have order, the magnitude doesn't matter, just the order applies. So you cannot use this arithmetically. You have ordinal data, and that's quite important to keep in mind. Then we have continuous data, and continuous data is what you commonly look at when you look at data. So if you have 100 patients or 100 subjects in your data set, and you have 100 different entries of 10K running times, for example, you have 100 different entries for each individual. How long did that individual run the 10K? So that would be a classical continuous data, or the weight of your 100 subjects, or the length, or the mass. That's all typically continuous data. Maybe bounded or unbounded, that means, does it, yes?
One could argue that for degree of disability also falls under this. It's just categorized in a way that can be numeric.
The performance scale, I mean. Yeah, where 4 was the disability and 0 was fully functional.
Right.
Yeah. What was the question again?
That was just a comment that would more accurately be in the continuous category. It's just broken up into discrete categories for convenience.
Why would it be continuous? Well, I know where you're going. Yes, good point. Good point. But you're moving ahead because so here, okay, so we have within bounds summarization. No. So what this implies is, so you have continuous data, you have performance from 0 to 100. That's what you mean. And when you categorize something, you basically categorize it within bounds and you categorize it within certain groups. So what you do, and we'll talk about this in 3 to 4 slides later, you discretize it. So you basically, you have 100 individuals, each of them has a certain kind of performance on a performance scale from 0 to 100. And you're defining categories in which you basically define a certain level of functionality. And you say like, okay, so that individual from 0 to 100 is at a very low performance scale. And you say, okay, so from 0 to 25, that's my almost disabled group. And from 90 to 100, that's the very fully functional group. So you create these categories and then you count the individual that fall in the respective category. That's how you basically discretize your continuous data, but it's a good point. But the source data is continuous. The consequence data is basically discrete. The order in which this discrete data, in which the categories present, that's ordinal. So that's the distinction. But it's a good point. It's a good point, and it's actually a tough point because you kind of have it reflected here, right? You have different categories, and these different categories are ordered, and that's when the nominal category of disease becomes an ordinal variable because it is now presented in a certain order from 1 to 5. It can also be treated if it's out of order, it's just 5 categories. It's just 5 levels of a nominally variable. If you bring it in order, it becomes an ordinal variable. If you have now individuals that qualify for a certain disease, then it becomes discrete data because it becomes counts. Does that make sense? I know it's as a concept a little tricky, but it's quite central. And when it comes to discretization, let's quickly finish up continuous. We're coming then to discretization. So we have, so this can be bounded or unbounded. So there are values that are not possible to have. Like if it comes to the weight of an individual, for example, you will not find a weight of 2,000 tons, pounds, whatsoever. So that will not be possible. So there are some natural bounds and there are some bounds by definition. Whereas the bounds by definition for analytic purposes are kind of very carefully to be chosen because it may be tricky to choose something that may alter your inference into your data. So that needs to be very thoroughly justified when you bound it or when you exclude quote unquote outliers. What's important to keep in mind is that all the values within these bounds that are defined are possible. So an individual can also be 80.123 kilograms and not just 80. So basically you can have decimals and every accurate measure will basically be counted. The magnitude matters and you can also apply arithmetic operations to it. When it comes to summarization, then we're going in that realm that Natanya mentioned. So this is where you come into discretization. So you always want to summarize data because if you have data of, let's say, 20,000 patients and you have that Excel spreadsheet open and you want to communicate what you see in this data to your colleague, you cannot show him 20,000 rows. So you need to find ways to summarize this and aggregate this in a way that you can communicate. And that's where summarization becomes very, very, very important. So you really need to do this for every data set. And the most elegant way, not only every data set, literally every variable needs to be very thoroughly inspected. So the first step that you have to go through when it comes to the final report is to look at this data in all possible ways and understand how does it distribute, what are the outliers, and what does that actually mean. So yeah, multiple options, numeric summary and graphical summary. And we will talk about this today. So one way to show data is by using graphs. So it's quite obviously what's wrong on this pie graph. Generally, and I know it's a very popular way of depiction, generally try to avoid pie charts and pie graphs. It's a very inaccurate way and not very informative generally to depict data. Reason for that is because if you have 4 groups, it will just present each other, but you can't compare the groups anymore. It's like, I don't know why pie charts are still so often seen and so popular, but it's generally statisticians hate them. And for good reasons. It's not really informative. What you really want to do, you want to create a graph that has a maximum of information and allows a maximum of comparability. So if you have 2 groups, you want to show these 2 groups right next to each other, where you can, with a bar graph, for example, that would be my choice of depicting this data, you can right away compare the 2 groups against each other. It's just much more informative. But we'll see that. Another way to summarize data is, and this is now where we're going towards discretization, is with frequency tables. Frequency tables is basically nothing else, but you take each frequency table in its purest form is you take each possible entry in a data set and you count how often that occurs. So for my undergrads, I show, for example, I have an example where it's volcanoes, countries that contain a certain number of volcanoes. You wouldn't believe how many countries have at least 1 volcano. So and then you count the countries and you depict the number of volcanoes in the country, and you depict next to it in the second column the numbers that contain 1 volcano, 2 volcanoes, 3 volcanoes, 4 volcanoes. It's a nice exercise, and it's a very good example actually. But basically, these frequency tables are also called contingency tables. So you have a certain criterion, you have a certain category, a nominal variable, an ordinal variable, and you count how often these category occurs in your continuous data. And that's basically how you summarize your continuous data. So it provides a total number. As an example, so you have in the clinical trial, in a perfect setting, you have a 50-50 distribution. You have equally many individuals in your treatment group as in your control group. These individuals are tested for the severity of pain. And that pain can be mild, moderate, or severe. And that's rated as, according to a certain pain level. If you quantify this, classical example is a pain scale from 0 to 10. And you would stratify this according to predefined categories that you defined before. And then you have mild, moderate, and severe. As per definition, you get then 3 categories. So now you're counting how many of your 100 subjects have now basically said they have mild pain, how many have said they have moderate pain, and how many have said they have severe pain. And that's the second part of this table. And now you can basically put this together. And that is a contingency table. It's a 3x2 table. So you have here 15 individual mild, 15 moderate, 20 severe. You have 5 mild, 15 moderate, and 30 severe in the control group. In what direction are you thinking when you look at this data already, in terms of inference just? You see no change in the mild group, not much different, but what you see is that you have more with severe pain in the control group. So that means the treatment hypothetically could be working, right? Just as an idea. So now we will be discussing in lecture 7 or so, we talk about chi-square testing, where you can test such an assumption statistically. What you will need for that is the so-called marginal totals. So that's basically just the sum of these 2 columns and these 3 rows. Based on this, you can calculate odds ratios and relative risks. And we will do this. Okay, so these are the marginal totals, and these are the marginal probabilities. With the marginal probabilities, you can then calculate a relative risk, because a risk is nothing else than a probability to have a certain condition. So here's 50 because it's in total 50. But basically, if you just calculate the probability of having severe pain in the control group, you can compare this risk to that risk in the intervention group. And that's essentially where you go into the realm of relative risks. And that's how you can compare risks against each other. But more about that later. So now we come to the graphical display. So this is really where we're starting to display things. I mentioned it before. Don't use pie charts, use bar charts. It's nicer because it allows you to automatically compare magnitudes of the percentages. You can also do stacked bar charts. Not my favorite, to be honest. I'd rather have the regular bar charts because you can hypothetically, you could also do bar charts and compare treatment and intervention right next to each other for each of those groups. But there are various ways. I'm not a particular big fan of stacked bar charts. Okay, summarization, frequency tables. What is important is so the discretization is basically done on various ways. So it can be, how should I say, arbitrary. So you can just say, okay, so mild is from 0 to 30, moderate is 30 to 50, and severe is 50 to 100. You can also do this population-based. Population-based means that you basically, you have 100 individuals. Well, let's make it simpler. Let's say it's 99, and you take 33, you define the 33 lowest as, so the lowest tertile as your mild group, the 33 next highest as your moderate, and the highest 33 as your severe pain. So that's another way. But then you need a large population. But basically, it's discretization. So you're stratifying it into categories, and then you're counting the occurrence of each respective category in your data. So that's discretization. And then you can treat it the same way as nominal and ordinal data. Obviously, if you create smaller bins, you get more categories, and then you get a larger table. So that goes without saying. Where you also need discretization is when you want to graphically depict continuous data. And this is what I mentioned before as a histogram. And this is one of the most important graphs in analysis. Whenever you start the analysis of a continuous variable, take the continuous variable and map it out as a histogram, because it shows so much information. It shows you where actually the bulk of your data is, where most of the people are located. It shows you all the outliers. Basically, when you then use markers of central tendency and variability, it also allows you to show different groupings. So you can see where actually you have an average located, where 50% of your data is located, left and right. So that's the median. And you can also apply then different vertical lines showing you the respective categories that you have defined in your data. So that's where it becomes very useful. And we will work on that code next class. What you can also do is you can create so-called frequency polygons. In its simplest form, it's basically just connecting the top of the bars with each other. In a more sophisticated form, and then the form that you can do it in R, it basically overlays it with a mathematical function. Then it looks smoother. So it's a smoothed frequency polygon. That's also yeah, that's the smoothed polygon, smooth probability density. And yeah, another way how to depict data is the so-called box plot. You can essentially, box plots are quite useful markers. So basically you have a box, you have whiskers. So it's also called a box whisker plot. So you basically, you have with the solid line in the middle, you have 50% of your data. That means left and right from that solid line. If you continue this all the way down, you would have 50% less than that point and 50% higher than that point. The outer ends, the outer lines of that box indicates 25 and 75 of the data. That means to the left of the lower rim of that box, you have 25% of data. You have 25% of data in between here, and you have the next 25% here. And then you have the universe that's greater beyond the upper rim. Exactly. The box in total is the middle 50%. What's important, this is also called the so-called interquartile range. So that's the IQR. And these whiskers indicate 1.5 times. So it's basically this point plus 1.5 times this IQR. And that's basically becomes the whisker. Everything exceeding that whisker becomes an outlier. So that's the definition here. Yeah, we'll talk about percentiles, but I will go quickly over that. So that's Q1, Q2, Q3, the median, interquartile range. That's Q3 plus 1.5 IQR. Okay. That is a strip chart. This will be seen in various contexts, but basically it gives you the same amount of information as a histogram, just in a different format. You don't see it just in a depiction like that. It's usually not replacing the histogram. I use strip charts when it comes to probability depiction. If you have like a whole range of data and you show probabilities, then you want to add as an additional information the population density. And this is SARS. Those of you that have done SARS may have seen a graph like that. And this is why I again like R, because I can customize things the way I want them. So you kind of you know already also here you have the numerical summarizations. Here you have a normal distribution curve, smooth polygon. You have a kernel, smooth polygon. You have confidence intervals here around the mean. You have a mean, you have a median, you have the box whisker, you have the outliers. So you have it all on one graph. It's a very busy graph. So if you show this at a presentation, you can speak about that graph for like 6 to 7 minutes probably. So it's sometimes less is more. So the summarization, you basically for nominal, this is the summarization slide. So you have for nominal and ordinal data, you have frequency tables and plots. For discrete and continuous data, you have frequency tables and plots, histograms, box plots, and frequency polygons. And without further discretization, you can have something that is called a scatter plot, which we will look at later on. And that's it for today. So that's the lecture piece of it. Any questions to any of this? I was a head start into what is data. If not, do you want to take a break or do you want to keep on going? Okay, let's keep on going. Okay, any questions on Zoom? If not, then let's get started. Okay. I'm gonna find a good position. Okay, so let's start with the following. So we have now all files in your module. So you have here a practice spreadsheet, you have an R code, you have a practice lab 1 and a practice lab 1.r. So docx is a Word file, as you all know. .r is an R code. So this R code is being loaded in our studio. So I suggest you have you build up a folder structure, which is preferably located on your desktop for now. You can move it later on when the class is over, but for now I would put it just on the desktop. I would label the class name in a folder in the folder structure. And then I would label it according to modules. So today we're starting off with module 1. And the reason why I'm suggesting that is because it is quite a few files. So you will get 3 to 4 files with each class. So it accumulates. The structure that you're developing now, that will accompany you for the entire semester. So it makes sense to kind of follow along. Good. So here we have the PPTX, that's the PowerPoint presentation. Here we have the Excel spreadsheet. The Excel spreadsheet contains some random data of 4 individuals that have 4 different ages over 4 different years that earned different amounts of data, different amounts of money for each of these years. So you see what one would refer to as a time series. What's important to keep in mind is that this would be continuous data, this would be categorical data, and this would again be continuous data. So this is essentially also then in the spreadsheet on R. So the only reason why I have the spreadsheet in, this is just more of a sandbox to play around with. So basically R Studio will, if you double click the module 1 R code, this will automatically open up. You can also open it by going on File, Open File, and you just find it in the respective folder, and you're just opening it. This R file is in essence nothing else but a text file. That's what it is. It is, you can, if you just click on the R file, it will basically display it as a text file. I don't know who of you is on Windows versus Mac. A Mac will automatically recognize it as a text file and would display it as such. Canvas does not, which is a little annoying. But for example, in Windows, you can just make a right click and open it in the text editor as well. But we want to have it in R. For R, so you have installed first R, that's base R. That's the actual core engine. That's basically the software. R Studio is basically nothing else but a compiler. R Studio is built around R. And R Studio is using R to run scripts. And it's always organized in the same fashion. So R Studio will be organized on the left lower quadrant. This is where R Studio organizes and leaves R. That's the default setting. You can change it, but I wouldn't recommend it. Then you have on the left top, you have the actual script. Right top, you have the environment. The environment is basically where all your objects are. Your objects can be data frames, your objects can be models, your objects can be t-tests, whatever you do, everything can be packed in an object and can be readily available for you to call it again and look at it again. In the same fashion, you can also write functions. Functions will also end up here. You can do various things that all can be updated if you update your data. And that's the beauty of it. And then you have here on the right lower quadrant, so there are various different tabs. The tabs we will be working with today is plots. So we're creating first graphs today, and you will see how to handle those in our. Any questions on this so far? I think it's simple for now. Okay, so we have now our data frame. So if you want to create a data frame yourself, you are building here different entries. You have DF is basically, that's my abbreviation and my acronym for data frame. You have here a smaller sign and a hyphen. That is basically equal to an equal sign. So basically you're telling R everything to the right of these two signs will go into what's left of the smaller sign. So we're basically saying here, this data frame, this whole madness that's written behind here, all these numbers, that basically should be packed into data frame. And you can run this line. So you can run lines in various formats. You can either go here on the right top, clicking on run, or you can just click anywhere, not selecting anything. That's important, not selecting anything. But if you're in the line and you press Control and Enter or Control and Return, it will run one line. It's jumped all the way down here because that's the next line that actually contains text. So, but it will jump each line and everything that belongs to that line. So that entire 2 to 5, that's actually one line of code. So R is, it is always a function oriented, but it's pretty much focused on each line. So it's not like SAS where you have like one function that contains like a million options. It's basically very bound to lines. So now we ran that line, and what we did was we built a data frame with 4 different variables. The variable name, age, year, and earning. And what we did here in the following, we assigned certain values to each of these variables. And these are basically listed after the C. C stands for concatenate. Concatenate basically puts all of this together and creates, as a consequence of that, it creates what is called a vector. A vector is basically a list of entries. So if I do, for example, I do a vector of 1, 2, 3, 4, 5. This is now a vector of these 5 numbers. So with C, you create these vectors, and you will learn all of this in data camp. So that's kind of the beginning exercises, but I'm just giving you a little bit of a head start here. So if you look at this data frame, that basically looks like that spreadsheet. Nothing different. Oops. Looks nothing different than the spreadsheet, contains the same data. What's different now is that you cannot click on a cell like you do in Excel. You need to address it. You need to tell R which cell are you interested in. And you can do this by basically telling R data frame. So I'm interested in DF, and then after that data frame, you give it a bracket, and you're basically stating in the bracket 2 things. Row is before the comma, then a comma, and then the column. So if you depict DF2, it will only show you DF, all the rows. Empty means all the rows. Give me all the rows. So there's no criterion, but the criterion for my column, which is after the comma, is I want the second column only. So these are all the ages because the age is the second column. Okay. If I want to be more specific now, and I only want the age of Nicole, I can add this with the apostrophes here. and I can say Nicole. Oh, not like this. Name equals Nicole. Now I only have all the entries for the age of Nicole. So what I'm saying here, I'm defining here a criterion. So I say df $name. That's how I'm addressing one variable in the data frame. And with the double equal, I indicates that this is a criterion that's coming now. So I can address each individual entry, each individual variable with df $, and here I have a menu that comes up already, and I can select here which one I'm interested in. So if I want to see year, I can do that. I run this line and I get all the years. I get the entire variable year. And I can utilize this to restrict the criterion of what I want to address. So if I want to say, for example, I can also do the following. I can say, for example, I can say df name equals Nicole. Two. Oh. I can also do display here the year in which it was recorded, or I can display her earnings. So you can individually address whatever you want to address. If I only want to have the first row, I need to log in here first row only, but for all my variables. So this is where I only see Teresa in 2018. And you can do these exercises for whatever combination you're interested in. You can here look for all earnings by Sarah. You have here df name equals Sarah and earning only. So here you have the earnings of Sarah. So this is basically how you can address each of these. So you can sum up all Sarah earnings. Sarah earnings is now all from Sarah, and you can sum this up. That's all that Sarah earned. So you can arithmetically manipulate. Yes. 14. 14 just shows the first row.
Just show all the name of the.
Yeah. So this is just the first row, which is basically horizontally. So the first entry before the comma gives you the row number, and the one after the comma gives you the columns. Yes.
Are the elements in the vector 0 one index? Like they start from 1?
They start from 1, yes. Well, in Python it's 0, right? Is it in Python 0? Or?
Yeah, and
Yeah, that will.
R and bash.
Yeah, no, that's just 1. Is 0? Hold on. Is 0 maybe the header? See that? I never tried. Yeah, no, it's. Now you have a separate command. You can do call names. So that's basically that's the headings. So you get like this. You get the headings. And you can also manipulate the headings that way. So you can say call names. You can change the call names. Specifically, if you say call names 3, for example, you only get the third entry for the column name. Nothing is better than the reaction of a Python user. It's funny because a friend of mine, she's a mathematician, she has the same reaction whenever I show an R syntax. Yeah. So there are subtle differences, which are for Python users tedious, but for me, it's the other way around, right? It's like if I look at a Python code, I'm like, oh, really? So it goes in both directions. Okay. Okay, so we can restrict this, for example, also for things like here depicting only the entries for 26-year-olds, which is here only applying for Sarah, so you're restricting whatever you're extracting based on criteria that you're predefining here. It's just blaze through that code a little bit. It kind of gives you a head start into what you're doing then in DataCamp. Good, but let's look into our actual R code for today. So for this purpose, we have a practice lab. Is it practice lab? No. We have a practice lab Word file. Okay. So we have two very interesting data examples today. So we have Dr. Arbuthnot. I was missing a U, good gentleman. Arbuthnot. So Dr. Arbuthnot was a physician in the 17th century, and he had the brilliant idea to document the counts of all girls that got baptized in the respective years. So back in the 17th century, there was actually quite an undertaking, I can imagine. But basically, we have this data. So we want to analyze this data, and we want to look at this data, and we want to compare it then with the data that's currently being recorded by the CDC. Not necessarily in terms of the count, because the count naturally has increased tremendously, but we want to see whether the ratio has changed, right? And all of these things you can do quite easily. So, so we're going to start off with Arbuthnot. So for this purpose, we're starting this line of code. Now, first, there's one more thing. So we talked about the folder structure. Please create in the module. So once you have created module 1, create a new folder and call this folder output. And I want to keep this separated for the good reason, because that's going to be the output folder moving forward. So whenever we create a new module folder, we create a new folder output, because whatever we are writing or we're plotting and graphing and then exporting as a PDF, we're going to put in the output folder. So you need to tell R where that output folder is. And this is usually where things are getting tricky. So thank God we're recording this. Remember this. So who's on Windows? Who's on Mac? Windows. Mac? Windows. All Windows. Okay, good. For Windows users, it's a little bit more tricky. Not necessarily that much trickier, but you'll see. Okay, so for Mac, it's easy. You make a right click on any file in the root folder and you press Option. What will happen is, and this is with the newer version, it shows you copy practice lab 1 as a path name. You copy this, you go into R, and you're overriding then whatever is here. That will automatically take you practice lab 1, you override practice lab 1 with output, and you make a slash. That's all that's needed, essentially. So again, you make a right click on the file, you press Option, it will change, copy that location to a path name, copy that path name into R, and you can use this right away. So if I were to define now my write folder with that output folder, I could do this right now. With Windows, it's a little bit more tricky. With Windows, you need to make a right click on the file. You need to go on Properties. And so I'm doing this here with Get Info, which is kind of the equivalent for Mac. You need then to go on Location on Windows, copy this location into Mac, into R. And this location will then contain a Windows-specific symbol, which is the so-called backslash. And you need to overwrite this backslashes. So all of the backslashes in this folder structure with a slash. So R does not like the backslash. So that's where it's a little bit tricky, but it's not terrible. It's four times replacing a backslash. So, but it will need to look in some shape or form exactly like it is presented here. So it will show you an exact folder structure, and you will compute the folder structure with another slash, and then you basically put it up here in line 4. So what we do here in line 4 is basically nothing else but as defining, you're defining here the right folder. So right folder is basically then, if you call right folder, it basically depicts your folder. So you're assigning that folder name to the object right folder. And you can utilize this in the following by basically automatically writing into that folder. And we will do that in a second. So this is basically how you first define your right folder. So here are 2 different lines that show you source, which is basically querying data from OpenIntro. So Arbuthnot and present data comes from OpenIntro. If you run these 2 lines, you will basically see there's a creation of 2 additional files in addition to our DF of the earnings of Nicole Zero and the other 2 individuals. So we have now with Arbuthnot, we have now 82 observations over 3 variables, where the first variable is year, second variable is boys, third variable is girls. So we want to do now a couple of things. So first of all, it asks us, what command would you use to extract just the counts of girls baptized? And that's basically this command on line 8. So if you just want to extract all the counts for girls, you just write Arbuthnot $girls. That will only get you the variable girls, right? Simple, just like we did before. If you want to summarize the girls, you basically can do this with the summary command. The summary command basically by default gives you a minimum entry, a maximum entry. It gives you the first quartile and the third quartile. You remember the box on the box plot? It gives you a median, which is the solid line on the box plot, and it gives you a mean. We're going to talk about it next class, but there's an inherent difference between median and mean. The mean, the arithmetic mean, is calculated by summing up all entries and dividing them by the number of occurrences, whereas the median stratifies your data into 50% above that value and 50% below. Of note, in a normal distribution, mean and median should be identical or preferably close to each other. If the mean is very far off, you probably have a lot of outliers or you have a skewness in one direction, but we'll talk about this next class. Good. Okay, summary. Okay, so now we want to know now the year in which okay. So we want to display the baptism records for girls, boys, children, the ratio of boys and girls, and the proportion of boys and girls. And this can be arithmetically quickly calculated. So here's another exercise. If you want to extract from your data the actual year in which you had a maximal number, the maximum number of girls born or children born, you can do this basically by Arbuthnot, again the bracket, where Arbuthnot girls is equal to max. So with max, you get the maximal entry. So if you have max Arbuthnot girls, This is one value, right? So this is the maximum number of girls that were born in a respective year. So now you want to have a depiction of Arbuthnot where girls, where the entry for girls was equal to max Arbuthnot girls, so to that value here. So essentially what you get is this. So this in 1705 with 8,366 boys and 7,797 girls, which was the year with the maximum number of girls. You can do the same thing with men. And you see in 1650, there were only 2,772 girls. So there was a substantial increase in the number of births per year. So this basically walks you through the same exercise here for all the children. First, we need to now calculate children. So we have, so children is quantified here as the sum of boys and girls. That gets us a new variable. So if you want to create new variables, you take the name of the data frame, you put a $sign, you call it children, and you give it the arithmetic operation that you want to perform right after your equal sign. So now calculating this gets you now the number for all children. So that's your new variable. Same you can do as with boys and girls. So these are the years with the maximum number of children. Now it's getting funner. So now we want to know the ratio of boys and girls. Same calculation again can be done for each year. And this is a specific thing for R and Python. If you give it a command and you say, okay, so create a new variable and do a certain mathematical operation with that variable versus that variable, it will always go from the first entry to the last entry. So it basically goes list-wise through your entire data set. So if you're defining here the computation of Arbuthnot boys and girls, it will automatically do this for the first year, for the second year, third year, fourth year, until the last of years in your observation period. And the same with the ratio. So if we are writing here, the ratio equals boys over girls, that will get you a ratio, which you can summarize here, basically with summary. So we have here in the median, there was slightly more, it was boys, girls, slightly more girls were born. No, less girls, sorry. Girls are the denominator. Slightly less girls born over the years. So you can do the same arithmetic, and now you can do the proportion. Keep in mind when you calculate proportion, also the difference between proportion and percentage, just for the terminology for the final report. A proportion is basically you have the amount of children, you know the number of children, you want to calculate the proportion of boys in this population of children. It's boys divided by children. That is the proportion. So this, I'm not doing it. So this is your proportion. So this is the proportion of boys. So as we've seen before with the ratio, there's a larger proportion of boys compared to girls. So there's approximately 51.5%. Because if you want to come from a proportion to percentage, you multiply it by 100. Just for the terminology, this is important to keep in mind, please. Okay. So now we're doing something else. Now we're creating our first plot. Any questions so far?
So if I control enter for code 27,
yeah,
showing class null mode null.
Just mode, I'm not sure. So it's usually easier if you maybe if you take your laptops out, because the second part of the practice lab is actually was meant to be done in class. Did you run the calculation of ratio first? You need to run the ratio first. No, you need to run this one, 26 first. Yeah, now it should work.
Sorry.
No worries. So what's also important when you calculate things, so you need to follow the order in the code, because just because it's written in the script, it's not automatically ran. So you need to run it line by line by line up until that point where you're actually calling that particular variable. So you need to first run it to the computation, and then you can run the actual summarization. So now we're basically getting to the plotting part. So plot is basically quite simply done by using the plot function. But again, this is base R. This is very simple calculations. So there are much fancier plots. There's a package called ggplot that you will see in the data camp, which is giving fancier plots and basically different aspects. So I'm still doing my base R plots, but so they are fancy. There's fancier plotting out there. Okay, so plot essentially is a regular simple scatter plot. It basically it has an y-axis and it has an x-axis. You give as the first entry, you're defining your x-axis, and on the x-axis you want your year. That's all you want. On the y-axis, you want to show the number of boys. And that's your second entry. Then with X lab and Y lab, you can basically label your axis. So if you have now, so we know that year, that's basically all the years of observation. Boys, that's the y-axis, that's the corresponding counts. Years is on the x-axis, and the birth is basically our y-axis. So if we're just running this, this will basically give us a list of our boys. Yeah, that's the next line, because if you want to stratify in two different groups, there are different ways to do that. One of the ways to do that is by basically adding now to this plot, in addition, the girls as points. And this is done here in red. So the girls are red. So that's how you add the girls. So now you can do the same exercise in, you can do the same exercise with boys and girls where you have children. You can also overlay it. So that's the count of children, because your y-axis is now boys and girls. Now you can do the same exercise with ratio, where you do the calculations of that ratio. Oh no, it's actually proportion, so sorry. So you can do this here. So that's the proportion of boys. I suppose this proportion. That's proportion of boys. Okay, yeah. And now we're getting to essentially the right folder. So the right folder is basically, so you remember how we defined the right folder all the way up there. Were you able to do it in Windows? It worked, as I said. And just replace the backslashes with slashes, that should be fine. The hiccup probably comes when we run the next line. But okay, so if you do PDF, paste right.folder, practice lab 1. So the reason why I do paste is because you're putting together commands to create this folder and file name structure. So if you run this, this is basically what it will put with the paste function. So with paste, you're giving it different fragments, you're pasting it together. and it basically amalgamates it to exactly what you want to be displayed. So that's your folder, and that's your file name, practicelab1.pdf. And the beauty of R and this kind of programming is that you can automatically export this plot as a PDF. And so you don't have to click on anything. So you can basically, with the PDF function and the curly brackets here, you can create a PDF. So this curly bracket and this curly bracket, they're basically related. This curly bracket and this curly bracket are basically related. And these two curly brackets basically define one page in your PDF. This one, another. This one, the third page. So you're creating pages in your PDF, and you're closing your PDF file with device off. That's when you shut off the plotting engine. And the way this looks like is by running 36 to 50, it will give you in the end our Studio GD2. These are all the engines it's closed. And if you go now into your output folder, you have here Practice Lab 1 PDF. And that's the PDF that you can then include in your report or in your paper, or you can include in your. I had a feeling that's what happened. What's the error?
The folder, the file has been created, but if I double click on this, there is an option. This file
Can you go back in the archive? Can you run the device off once again? Yeah, now it should appear. Sometimes a little tricky. No, still not. Can you run this again? Run the device off again. Okay. No, let's try again. It's usually a problem with the plotting engine. But you need to run it again from the beginning. So run the device off first, or restart. Yeah, exactly. But run device off first once again, just to make sure. This is usually that's the most common hiccup. So now it's closed.
So,
and now just run 36 to 50. Yeah, was in. Okay. Now let's check again. So that should work now. So, and the second part of the practice lab is now to repeat the same exercise, and this is perfect. Okay. And this is now, while it was the device was still open. I don't know why the plotting engine was active. So now the second part of the practice lab is to basically to run this again in the CDC data. And so this is then becomes, well, only 5 minutes left, but the submission would then be arbuthnot and the CDC data. So the only thing you need to do here is to basically repeat these computations with the CDC data. So you're loading the CDC data, and you basically you're replacing arbuthnot with CDC. So the CDC has the same folder structure. Oh. So present. Oh, present, not CDC. So here you have again year, boys and girls. So the only thing you need to do, you need to create a second script, or you add it at the end of the script, and you replace all the arbuthnot entries. So every time it's written arbuthnot, you basically replace with present. So it has the same column name. So you just need to adapt it. So that should be fairly simple, right? And just maybe copy the arbuthnot code here from 52 onwards, and just repeat it with the present data. That should be a simple exercise. Get you started a little bit with R. So the final deliverable, and that's for submission, will be if you press Control and A or Command and A for the Mac users, it will select the entire code. If you press now Control and Enter, it will run the entire code through. And basically, two things. So first, clean the entire console with Control and L. With Control and L, this is all empty. If you press then Command and A and you select everything and you press Control and Enter, it will run it all. And then please select in the console everything that you just ran. Press Command and C, copy it, go on Spotlight or create alternatively in Windows a text file. And so for the Mac users, it's in text edit. You create a new document and you copy paste it in here. You save it as BTM6000, your family name, and practice lab 1. And that's submit via Canvas, please. Simple, right? No.
Do you want the PDF file?
Yes, please. Yeah. Yeah. Good idea. Thank you. All right. Any questions? A simple exercise. Gets you started on R a bit. All right. Good. If questions, discussion board, and shoot me a heads up email that I can respond to the discussion board if I don't within a day. All right. Thanks so much for your attention. And yeah, nice to meet you all. Looking forward to the summer semester. We're going to have fun in R. Okay. Any questions on Zoom?